SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We have already started to discuss about mineral deposits which form primarily by sedimentary processes. Since we have sedimentary rocks arising out of detrital processes, chemogenic processes and biogenic processes, so there are deposits which can be assigned as deposits from detrital sedimentary processes, chemogenic sedimentary processes and biogenic sedimentary processes. We will be restricting ourselves to discussing the first two types, and we already started to discuss about an important class of deposits which are the iron formations, the banded iron formations, essentially referring to the type of rock which primarily have a banded appearance, and they contribute the majority of the iron resources to the world and distributed in the cratonic and older cratonic blocks of almost all the continents. So these are this is on the right, this is a photograph from the Hammersley Basin in Western Australia, where you could see a iron mine which is quite big, almost like constituting a series of hillocks there, and the left hand side is a exposure scale photograph of what typically known as the banded hematite jasper, or there the way they occur and the banded nature is very clear from the photograph. They are distributed in the, as I told, in the most of the older cratonic blocks, Precambrian cratonic blocks like Western Australia, the Hammersley Basin, the Superior Province in Canada, Labrador Trough in Canada, the Quadrilateral Ferrifero in Minas Gerais in Brazil, in the Transvaal supergroup South Africa, Krivoy Rog in Ukraine, and the Iron Ore Province in the Singhbhum Odisha region in India, Baladila Basin in the Mackenzie Mountain in Rapitan Group Canada, and the Damara supergroup Namibia. So these banded iron formations, which contribute to the majority of the world iron ore production, primarily are old deposits, Precambrian deposits spanning from mid to late Archean to late Proterozoic, almost of the age of 800 million years. And the deposits which are in the Mackenzie Mountain belonging to the Rapitan group and the Damara supergroup belong to this the youngest of the iron formations of the world. So these deposits have generated huge interests amongst the ore geologists. They have been extensively studied, and voluminous literature have been written on these deposits, addressing the very issues of their origin. And there are some very intriguing issues, such as the very fact that such kind of extensive occurrences of iron ores in the form of the banded iron formations, with lateral extent sometimes to going to hundreds of kilometers, they don't have much of the younger counterparts in the later part of the geologic history. So it's a little intriguing and tricky at the same time, because we don't see the modern day processes as analogs to the old deposits. So we'll just it will be difficult to give a very detailed review or detailed idea about these deposits, because they are older deposits. They have been subjected to a lot of later processes in the respective cratonic blocks. Their characteristics, constitution have been modified to great extents, and that's the primary reason why many different ideas on their origin, many different hypotheses have been proposed. We will be giving a brief overview of their characteristics and what we could infer from those characteristics, and as far as their origin and the understanding the process is concerned. Here have a brief idea about the three different types. The one which are the oldest amongst this among the members is the Algoma type, which occur in the Algoma basin in Canada, and the superior type and the Rapitan type. As you could see, the age ranges is dominantly superior type is dominantly mid to early to mid Proterozoic, and the Rapitan type is nearly going to the Neo-Proterozoic time, ending up at 700 million years. So, as far as the dimension are concerned, the most extensive type are the superior type. They are stratiform, and they are thick, almost of the extent of 100 meters or more in thick, traceable for hundreds of kilometers, as against the Algoma type, which are mostly occurring in the greenstones, old greenstone belts. They occur in lenticular bodies, just about meters to tens of meters thick and a few kilometers in lateral extent. And the Rapitan type are more or less comparable to the superior type, but are very characteristic in their lithological assemblages with very little volcanic component in the succession and they occur at the base of the basin. They overlie the basement rock, and the superior type, they generally are interpreted to be occurring in the stable shelf in the marginal basins, and the Algoma type are in the greenstone belts, which are extensively deformed, metamorphosed, and we see them in the old greenstone belts in many parts, as I have said. And so that is how the Algoma type have a very intimate association with volcanics, with seafloor rocks of basaltic composition now present as amphibolitic rocks, and they are associated with the oldest of the units of the greenstones. And the superior type do have volcanic component, minor but always present in the succession, and sometimes they preserve the entire sedimentary succession from the basement to the youngest of the formations have been worked out in many deposits. And the Rapitans do have a glaciogenic component with them, and they are the marstone, they are associated with the marstone, shales and conglomerate. And mineralogically, this Algoma type are dominated by oxides, mostly magnetite, carbonate and sulfide. The superior type also have similar mineralogical association, mineralogical constitution, whereas the Rapitan type mostly dominantly oxide. There has been a looking at the way these iron formations they occur in different parts. It's observed that from the constitution point of view, we can see that they are occurring in different compositional variations, which we call them as facies of the banded iron formation. And these facies are generally they are chemically controlled, because we are essentially dealing with the sedimentary process which is chemogenic in nature. And these facies, which we are dividing as oxide facies, which is dominated by magnetite hematite, carbonate facies, sulfide facies, and the silicate facies. The silicate facies is characterized by the different types of ferruginous clays, minnesotite and granulite and kind of clay minerals. And the sulfide facies is dominantly of pyrite, almost like pyritic black shales. And what is interesting is that this division into the facies and the occurrence of these banded iron formations in different mineralogical constitution can be explained chemically, and that's how we generally try to see or interpret them in terms of the variation of the oxidation state of the environment, of the aqueous environment, and the pH, that is the acidity, or as we say the activity of the hydrogen ion concentration. These two parameters, because they are surface processes, surface operating on the continental shelf region or somewhere in any intercontinental basin, so their conditions will be to near surface condition of 25 degrees centigrade, and we can see or characterize the environment chemically by using these parameters, which is basically the EH and pH. Even though you would be basically giving the details in supporting notes, I would just like to make a simple sketch on how this kind of a EH pH diagram can be constructed. So, the dominant species we can consider the iron to be in iron 2 plus, that is the state in which the iron is soluble, and the iron 3 plus, that is the state in which it is insoluble, and we could consider the dominant mineralogy of the facies that we have just stated. Fe2O3, that is hematite, Fe3O4, that is magnetite, FeCO3, that is siderite, FeS2, that is pyrite. So, we could relate them by some simple reactions. For example, these are all coming from very simple principles that we studied in our textbooks of chemistry, high school textbooks in chemistry. If I write a reaction, simple reaction like Fe2 plus giving rise to Fe3 plus 1 electron, this becomes a reaction, a redox reaction, which can be worked out, and based on the free energy change of this reaction and using the simple Nernst type equation, which gives me EH is equal to E0 plus 2.303 RT by NF into log of K. So, in most of the cases this N stands for the number of electrons involved, and F is the Faraday constant, which is about 23.1 kilocalorie, and this E0 comes from the standard state free energy change of this reaction, which is the del G0 divided by RT, sorry, del G0 by NF, and here the N and F are the same. So, we could by working out these kind of reactions like the one which I mentioned here, or say for example, I will just first draw the rough boundary as they look like. The pH would be somewhere around 0.8, which is expressed as volt, and coming from say almost like minus 0.6 to 1.1 or 1.2, and this EH pH this is 0. Are basically bounded by the lower saturation, lower surface limit and the upper limit of the aqueous environment. This is defined by H2 to H plus, or we can say H2 to H2O, and this would be H2O to O2, and pH of about 4, roughly 4 to 9, So, this kind of boundary is defined for the natural limit of EHPH, and if we see, I am just making the very schematic, this is Fe2 plus, this is Fe3 plus, this is the stability field of hematite, this is the stability field of hematite, this is stability field of magnetite, this area which is bound by here and here, both this part are the stability field of siderite, and this is the stability field of pyrite, FeS2. So, generally this banded iron formation facies can be interpreted by using this kind of diagrams, which can be worked out at 25 degrees Celsius and 1 atmosphere pressure, and simple reactions like Fe2 plus water, Fe2O3 plus C6H plus 2E, where it is balanced. So, this makes a redox reaction which can be plotted. As you could see that if we work out this reaction, which will the details calculation will be given, if this reaction is worked out and the EH-PH relationship is found out, we can always have a EH will be equal to E0 plus 0.059 into pH, or we can almost like a straight line equation, we can put it EH is equal to A0 plus A1 pH, where these are the parameters which are coming from the E0 which is by del G0 of the reaction by NF, and A1 is coming from the equilibrium constant other species which are considered. And when we consider such kind of diagram, the relative positions of the boundaries are very much sensitive to the concentration of the different species that we are considering. The iron species in total iron content of the aqueous environment, then concentration of the carbon dioxide, total sigma carbon dioxide of the environment, and the sulfurous species. Depending on that, we can have the stability fields of the species, and we can interpret that if we are somewhere in an Fe2 plus stability field, then if we increase the this is a situation in which I can say that it is silica poor or silica deficient. The moment the situation becomes silica enriched, this will be replaced by some iron bearing silicate phase, and we see that with this help of this diagram we are able to explain the different phases of banded iron formation, in what kind of EH-PH condition we will have from iron 2 plus to Fe2O3 which is hematite, and iron carbonate and sulfide to be stable in restricted environmental parameters, which could be correlated to the conditions in which these rocks are likely to have formed in nature. Interesting thing is that these deposits, which are older deposits, Precambrian deposits, the age ranges as we have stated, these deposits are definitely subjected to metamorphism, and at different places the metamorphism grade could be variable. sometimes very high grade conditions from 700-750 degrees centigrade to 10-11 kilobar pressure have been interpreted in some of the Algoma type deposits, and some of the superior type deposits have also been worked out, but some of them retain their unmetamorphosed characters with the lithological characteristics like the shales and all within the different stratigraphic horizon persisting. And it's believed that in an aqueous environment, when this iron species, as we showed here, when they are precipitating from aqueous environment, it's very likely that instead of they being shown as oxide species, they would be actually be forming the hydrated oxide species, such as something like goethite, FeOOH, in different forms of this alpha beta gamma form of this hydrated oxides, which generally are named by as goethite or other hydrous minerals. And what we see them in the form of the oxide species is presented mostly as magnetite and hematite. Some believe that they are product of metamorphism, but the way the extensive occurrence and persistent lateral extension that we see them, they don't seem to be, in majority of the cases, they don't seem to be product of metamorphism. At the most, we can think of a very low grade from the silicate associated silicates, which we interpret in terms of going from very low grade to low grade diagenetic kind of environment, where these hydrated iron minerals might get dehydrated, and we get them in the form of hematite and magnetite. And then the diagrams, the pictures that we have seen about this iron ore, it would look like that the iron content of them would not be that very high, because going by the definition, something which is more than about 17%, 25% iron in this material, which we see them in the form of banded hematite jasper, banded hematite magnetite, or banded hematite quartzite, but we can only get them in the high grade, means the values going to 55%, 56%, or even sometimes a very high grade ore that we label them. So we need to have these deposits somehow enriched in secondary processes. So secondary enrichment processes are also visualized in case of these many of these deposits, and they are definitely quite variable, going from different terrain to terrain, or different areas, different basin to different basin. So it's a common attribute of them. Now, while addressing the issues of the origin of this iron ore, the most interesting aspects are that we see them, they are pretty extensive, huge quantity of iron being mobilized. So the very basic question arises that what could be the source of this iron? And as we discussed earlier during the introductory sessions, the temporal while discussing the temporal distribution of the various types of mineral deposits, we recalled that as per one of the hypotheses, the origin this to begin with, the atmosphere was much more rich in carbon dioxide, and the surface water was hotter and corrosive, and a bit different from what the system prevailing conditions at the present time, with the partial pressure of oxygen having the value of about 0.2. It was not so in the Precambrian time. So the two different sources for this iron, one could be the obvious choice could be detrite, to be continental. That means this, because of the continental erosion, the iron is derived either by chemically by transporting them in the dissolved form or in the particulate form. Since we see them in chemogenic sediments, so we can rule out more or less the detrital form of the transportation. Chemical form of transportation look to be more reasonable. But then if we do some calculations, say for example, take say simple example of a basin like Hammersley Basin, where we know how much of iron has been deposited there. So if we think that they have been derived from the continental sources, if we calculate the total concentration a total amount of iron that is present there, and the time duration in which this Hammersley basin has formed, let us say it is about 6 million years or so, then the rate of iron input to the and considering the fact they are deposited in the ocean basin in the shallow continental shelf region where it's the environment is pretty oxygenated, then the amount of input of iron that would be required per year would far exceed the present day rate of input of the metal in dissolved form, and by considering any major river system of the world, let us say Mississippi river system. But that could possibly be accommodated, that well it could be because of the atmosphere was more corrosive, more of iron was dissolved in the surface water, and but still the mass balance constant will always be there as a concern. The other possible source is marine, that is the sediments that are deposited in the marine basins. It could be the marine sediments who are getting deposited, or it could be the oceanic crust. Again, this we can also get down into doing some kind of calculation on the possible sources from the sea water, because essentially they are marine deposits and they must have formed in some way. If we consider that there, and then one of the most obvious sources of this iron that we can have in the sea floor is the sea floor basalt itself, which will be able to contribute the iron by in the process of reaction with the seawater, and we already have stated that the seawater during that time was more carbon dioxide charged, more corrosive, with more of acidity, and more of iron could be held in that in solution, and the process could be visualized, and then when we calculate we find somehow it is reasonable from the present day value of the seawater iron concentration, which is about 0.02 to 0.03 milligram per liter, and if that even going to some value as even a higher concentration that could have been there in the corrosive sea at that point of time, we generally kind of think of a picture like this. This is the sea surface, this is the sea. So what we see here, the sediments, this is generally the domain in which the oxide facies is forming. Then this is the carbonate facies, and this goes to the deeper part in which we are supposed to be getting the sulphide facies. And the model that we are thinking here, that the ocean water is having substantial amount of iron dissolved in the lower part, in the deeper part where the condition is very reducing. So, and then there must be some process of upwelling of this fluid, which is of the seawater, which is having a very high concentration of iron, and then when it encounters the more oxidative environment in the shelf region, then the iron is precipitating, which very much fits to the conditions of deposition in shallow shelf conditions. So the hypothesis that the iron metal is derived by the sea floor, or the sea floor basalt, sea floor rocks, with some input possibly coming from the sea floor sediments, look to be feasible, and this kind of model can be proposed for the origin of this banded iron formation. So we will continue discussing the iron formations in the next class. Thank you.